The first thing I'm going to look at in this first episode is this HP spectrum analyzer, this 8591A here. This unit here can go from 9 kilohertz, which is just about the limit of audible range, all the way up to 1.8 gigahertz. Now, even though that sounds like a lot, 1.8 gigahertz is pretty high frequency. It's above all of the radio brands that you might use in your car, for example. It's not actually that high when you get into scientific applications. So later on, I'm going to look at a 20 gigahertz upper range spectrum analyzer and repair that. Now you'll notice I have two of them. So I have this one here. This is the one that I bought. When I bought it, it was in working condition. And then I used it for the first time and it stopped working. So I can tell you what happened, and I'll show you the output of it, or what it looks like now in its broken condition. I have a pretty good idea. I've blown something in the input stage of this spectrum analyzer. So what I did was I looked for a parts unit on eBay. Now this parts unit here is actually missing the display. You can probably see some of the internals of it through the window. But from what I saw online, it actually still has its front analog section and all of the bits that I think I might have broken in this one. Now the problem with this unit here is actually, even if you connect its input to its calibration output here, this 300 megahertz calibration output, you see nothing. Now what you're meant to see is a comb. So you're meant to see a spike at 300 megahertz, 600 megahertz, 900 megahertz, and so on. But we see nothing at the moment. So what we're going to do is we're going to try and poke around with the front end of this, perhaps replace it with the front end from this, and see if it starts to work. And the problem is that's going to completely break the alignment, so we're going to have to kind of dig into it a bit deeper, find out what actually is broken, only replace that, and then maybe try and realign the thing. I do these videos because I think the best way to learn something is to try and teach it, so let's try and learn something together today. So looking from the top, this is the front here. From the top you can see the top case of the display. It's just unplugging it here. So this is the CRT display, so there's a lot of high voltage in there. Fortunately we know that that's working, so we don't have to go digging around in there. We also have the power supply up here, and at the back we have a board, a back plane, and then we have one large PCB here. Now this PCB here they call the analog board, and that's because it generates some analog voltages to control some of the RF circuitry that you can see. Now the RF part of this unit is this assembly here, this whole front assembly here, and then these boards that you see are lined up here in the back. And what happens is the signal comes in, it is mixed in this is the first mixer, before being isolated and filtered, and entering into the second mixer, before then being sent into the third converter here. So this is your first converter, your second converter, followed by your third converter. So before I get into the repair of the HP 891A, I thought I'd explain how it works, so that when we go through the front end, it makes a lot more sense that what we're looking at, these blocks of metal, actually have a physical purpose. So what I thought I'd do is explain how a spectrum analyzer works. Now a spectrum analyzer actually analyzes the spectrum. So what that means is it gives you a power versus frequency chart. Now what it does is it's taken in your normal time domain signals, so this is what you'd see on an oscilloscope, where you have what almost would look like random noise, and that's because inside there you'd see, if you put an antenna on your spectrum analyzer, you'd see things like terrestrial television, you'd see things like your radio background noise of the universe, and other sources like that. And then what it does is it tunes to a particular frequency, and once you've got that particular frequency isolated, you measure the power on it. And so what a spectrum analyzer does is it scans through these frequencies, moving this back and forth, the dial back and forth on your tuner, and it measures the power at each one of those points. So you might have down here, you might have something like radio, and up here you'll have something like microwave transmissions, say. Now, how a spectrum analyzer does this, it's quite hard to actually build something, a tuner, that is, say, a filter, like a selectable filter, that actually you can move around in frequency. So you couldn't, the idea might be that you build a bandpass filter out of capacitors and op amps maybe, and and use that, vary the capacitance, vary the resistance to actually select out a particular frequency. But that's actually quite hard. So instead, what's done in almost all radios is we use something called a super-heterodyne converter. And how that works is you have something, this basic block here, which is an RF mixer. And what happens is you mix the radio frequency signal that you're interested in with a local oscillated signal. So this comes in together and it leaves out the mixer here, and it forms what we call an intermediate frequency. But it doesn't actually just form an intermediate frequency. What you get out through this mixer is you'll actually get the RF signal itself, you'll also get the LO, and then what you get, the key thing is, are the mixing products. So you're going to see additional spikes, spurs, well they're not spurs because they're not spurious signals, they're actually things we're trying to make. But you'll see additional signals, say, at kind of differences in those frequencies. So those frequencies, the RF and the LO, will beat together and form a second frequency. And one of them will be, for example, at the LO minus the RF frequency, and another one will be at the LO plus RF. And actually you get them at all integer kind of multiples of them. So you can have, you know, the LO plus twice the RF or minus twice the RF and so on. However, usually mixers are optimized to produce very strong first order products, you know, so LO minus RF and LO plus RF, and they try not to produce any of the others if they can. Now, what we can do then, by varying this LO frequency here, we can make a different part of the RF spectrum appear at one frequency. So let's be clear here. If we were interested in the 0 kilohertz region, it's actually 9 kilohertz on this unit that's the bottom, but we'll say it's 0 for now, 0 gigahertz, yeah? If we were interested in 0 gigahertz, we might set our LO to 2.124 gigahertz, and what that means is our first LO minus RF, our first mixing product, is going to appear at 2.124 gigahertz. It's going to be the local oscillator. But if I move up to the top of the range, 1.8 gigahertz, and at the same time move my LO up to 3.9124 gigahertz, then again, I'm going to produce a mixing product at 2.124 gigahertz. So what's happening here is I'm not actually moving the RF up and down, but I'm moving the frequency I'm interested in. I'm saying the RF frequency I'm interested in, and I'm changing the LO so that that frequency mixes and produces a spike at this LO minus RF frequency. And that's what we call the intermediate frequency. So for this HP 8591A, the intermediate frequency is this 2.124 gigahertz. And there's a good reason why it's chosen to be there. Because if you look at the power versus frequency chart that I have here, you can see our RF signal falls in this range between 9 kilohertz and 1.8 gigahertz. And our LO frequency actually occupies the band above it. And in the middle is the IF. And the reason why we always want to make this IF fall in the middle between these two is we want to build a filter, a bandpass filter around about the IF, and really never see this RF signal get into the range of this. So we're basically designing this mixer to make our filtering job next, our follow-on filter, as easy as possible. So we want to be able to filter out one signal, just the IF, this LO minus RF frequency, and never accidentally have the LO drift into it or the RF drift into it. But what you'll notice is actually the LO does, the very bottom end of the LO, the local oscillator, is actually at that intermediate frequency. And so one of the things you'll notice on these 8591As is you'll see a large spike at about 0 hertz, and that is actually you picking up on the LO oscillator signal just bleeding through this mixer and making a fake, you know, intermediate frequency. It's not actually the radio frequency. Okay, so the whole idea here is that we're converting this RF and a frequency of interest by mixing it with an LO to form an intermediate frequency. Now what this mixer looks like is it's a pair of diodes back to back. And that mixes that's what's used, those are the nonlinear devices that you use to actually mix and form these products here. Now, if you've blown up a spectrum analyzer, the chances are you've overloaded the pair of diodes in that first mixer somehow. So I put a DC signal in. As far as I can see, there's a DC block. So I think the reason why I've blown this up is I've actually put too large of an AC signal, too large of an RF signal in, and blown up those first two diodes. So the first thing I'm going to do is take a look at that first mixer and just measure the diodes that are there and just see if they have a forward voltage, or if they've shorted out, or if they're an open circuit. And that'll help tell me if that first set of mixing diodes is gone. There are a couple of other stages though. So of course, once I've gotten to this 2.124 gigahertz, that's the frequency, that's the only frequency I have to care about once I've gone through this mixer here. I control the frequency I'm interested in by varying the LO frequency. But processing, as far as signal processing goes, I only care about 2.124 gigahertz. I'm now going to down convert that into something I can actually handle. So this is still quite high into the RF region, where we start to need RF magic to handle this signal. So the next stages that we will have on our spectrum analyzer are down converters to get it into a much more manageable frequency range. And actually the first stage of down conversion uses another mixer, and it mixes in a 1.8 gigahertz signal is in the second stage, yeah? And what, of course, if you look here, this minus this is going to lead me to a 324 megahertz signal. And so that's the second IF, yeah? And then after that, I actually have a third stage of mixing where we actually mix it with a 300 megahertz signal, and that then of course forms my 20. I've got it a little bit wrong. I think it's 321.4 megahertz. So I need an extra one in all of my math up here. Yeah. So there's just an extra one there. So it mixes down in the third mixer. The intermediate frequency is 21.4 megahertz, and at that point we can now attach our detector. So what our detector is it's always, we can optimize our entire circuitry and our detector circuitry to actually operate at 21.4 megahertz. And what it will be is it's either going to be something simple like a heater, and we measure the thermal energy, so we measure the temperature of this thing. So you reroute the signal in and you measure the heating power of it, or it's going to be something simple like a rectifier, and then we measure the RMS of the wave or something like that. Nowadays, I believe they're all diode rectifiers, but in the olden times, you could use things like these heaters. Okay, so let's take a look inside the spectrum analyzer and follow the signal path and see if we can find this first mixer, and then have a look inside it and see if it's broken. Okay, now, I think it's something in here that was broken, and I was pretty sure that something in here was broken, because what I was doing when I used this for the first time, I was monitoring a DC voltage, quite a high DC voltage. Not high enough to actually go beyond the limits of the input of this port, because this spectrum analyzer does actually take DC voltages up to 25 volts, and I was looking at a 10 volts DC signal. But maybe the frequency and the power of the noise that I was looking at was actually too high and overwhelmed some part of this circuit here. And it's likely to be some of this first circuit, because there's quite a lot of stages in this front section here before it gets to this rear section here. So I had a good idea. I guessed that this front end was bad. So what I did was I pulled the analog front section out from the parts unit and I replaced them. If I turn this on, it's going to scan horribly. I've noticed this in the camera already. You get this very slow scanning across here, so sorry about that. But what you can see is, with a cable connected from the calibration out to the input, what you can see here is a comb of frequencies. So this calibration output says 300 megahertz, and that's the fundamental frequency of this. But there are harmonics at multiples, integer multiples of this. So if I just hit peak search, this peak search button here, you can see my marker appears at the top of this peak, and it says 306 megahertz. And if I then go next peak right, you can see 600 megahertz. Okay, so now that the system's kind of working, is that it? Is it all done? Well, the answer is no. It would be a very nice short video if it was. But by replacing this front section here, I've dramatically altered the response of this unit. So I've replaced everything in that front assembly, and that front assembly includes the attenuator, the first converter, the second converter, Yig tune or oscillator, and I think that's it. It doesn't include the third converter. All of this is at the back of the unit. So if you have a look, if I actually replace all of that, a lot of this can be adjusted via this cal frequency, cal amplitude adjustment routine. Now these are routines that you can run from the front panel. You just connect the calibrator output in to the input and run this. It takes about, I don't know, 10 minutes to run, and it adjusts everything. However, these adjustments here, the frequency response and the second converter response, are procedures from the service manual that require external equipment, namely synthesizers with accurate level control. And unfortunately, I don't have those. So the frequency response, I could probably jury rig something that would work for that, but the second converter, I can't. And so I really want to avoid having to replace the second converter if I can, and preferentially I want to avoid replacing the first converter if I can, because I just don't want to have to do these procedures or borrow the equipment, try and find the equipment to do these. It would be ideal if something else was broken, say the attenuator or the Yig tuned oscillator, because these things mean I can just adjust as they are. I should still probably, given the age of the equipment, go through these verification tests, but again, you need quite a lot of equipment to do that I just don't have yet. So right, so the whole aim now is to find out which item's blown, and hopefully it's either the attenuator or the Yig-tuned oscillator, so that I don't have to do these adjustments. I wanted to actually have a look at the first converter assembly. So actually this is where we have a mixer. So we have our RF comes in just after it's come from the attenuator, and we mix in the LO, and that gives us our intermediate frequency. So our local oscillator, that Yig oscillator we took a look at, comes in here, and then the intermediate frequency comes out here. Now interestingly, there's the counter lock out here, LO out here, so this actually goes out to your RF counter that actually measures the frequency of the LO. So there must be a power splitter in here. The LO must come in, split, come out to this counter lock, and then what's interesting to see here is there's a terminated output here, which is the tracking gen LO out. So if I wanted to actually add a tracking generator to this, I would actually have to get this out to the front panel, and there is a space to actually do that. You can actually put, well, there isn't actually a space for this, sorry, I thought there was, that you could get the LO out here, but there's a space for a tracking generator. But what I could do is I could take this out, maybe to the back or the front, and then use an external tracking generator, which you can buy on eBay. And so I'm thinking about doing that. You'd have to terminate it whenever you didn't use the tracking generator, but it's a nice little addition to this unit. Okay, so I've actually tried unscrewing this, and you'll notice you have to take a whole heap of screws out. And once it's there, you lever it a little just to break the seal, and out comes the bottom part, which is just the case. And over here, what we see as we turn it over, so LO on the right hand side becomes LO on the left hand side, and your IF out, intermediate frequency out there, is in the top right. So what do we see? So first of all, we can see the RF in here. It then passes through a series of filters before it then enters this region here. In here you're seeing your intermediate frequency out. So this must be the mixer section here. And over here what you have is, oh, let me just check. One of these is, yeah, so your LO comes in at the top, and then it comes through these blocks, is split, and sent out to these two units here. But that's a bit strange, isn't it? So it actually comes to the tracking generator out and then carries on to the other unit. Now what's there is quite interesting, so let's see if we can get a bit of a close-up. I was worried that I'd blown the mixer section, so yeah, that's that part. Just right, so this part here must be the mixer section, and I'd blown it. I worried I'd blown it, and so what I thought I would have to do here is actually replace some diodes actually in the front mixer, but I can't see diodes here. I can only see this bit of rigid coax, and then this C2 component, which actually might be the diodes themselves. So I don't know if you can see this very well. Yeah, there's this C2 component. That must actually be the mixer. So funnily enough, I'd actually bought some match diodes. Here they are. So these are a set of match diodes that were recommended for replacing mixers. And so you get a match set of 4. I only need 2 for the mixer, but they came in packs of 4. But now looking at this first mixer, I think I would have to actually do something about this little RF choke here. So my meter is in diode mode, and what I'm going to do is just check. Okay, I can try connecting to this point here and this point here, and what you can see there is 0.277, and then I can try connecting to this point here, 277, and it looks like the diodes are okay on there. So I don't think that mixer is misbehaving, which is good news. So it looks like I've probably blown the attenuator and not the mixer as I thought I had. Well, that's good news for me. I can't really work with these RF things anyway, so it was going to be a complete guess. Alright, let's try reassembling the first front section. So let's take a look at this front assembly and try and figure out what's wrong with it. So first of all, I'll give you a quick tour over what's actually in here and how it was laid out when it's inside the analyzer. So first of all, there's this piece of hard coax. This connects to the front panel connector, and then it takes that end connector in, the signal in, and into this first attenuator, and the first attenuator sits underneath in here. It's a WaveTech attenuator. It has 3 separate electrically controlled attenuators within the side of it. There's a 10 dB, a 20 dB, and a 30 dB attenuator. You control those by pulling this pin to 14 volts, and if you want to disable an attenuator, you pull these pins low. So that means actually, as it stands right now, this is a 60 dB attenuator, unless I actually apply some power to this. You'll notice that the sticker says coupled AC and coupled DC, so the back end of this, which is actually connected to the front of the machine, is actually DC blocked from the rest of it. So if you pop your multimeter on here, you measure, I think, 1000 nanofarad capacitance on there. So there's a capacitor in here to block DC coming through. So this is where we get our DC protection from on the whole system. It also should be noted that when you're operating the analyzer, it never disables this 10 dB attenuator. It's always there. So you have to actually manually disable the 10 dB attenuator if you want to turn it off. And generally speaking, it's probably a bad idea. I mean, unless you're really searching for very small signals, you're protecting your analyzer with this 10 dB attenuator. Now, this is obviously the first thing, so if I've blown this up, I thought maybe I've blown up the attenuator. So how do I check that? Well, I could take my spectrum analyzer and attach its calibration output into this, and then put the actual output into the front end of the spectrum analyzer. And because it's working, well enough, I can actually see if that comb generator, those 300 megahertz and harmonics get through this attenuator, and then try disabling it. But I have a slightly better piece of equipment for that. Well, not better, but kind of nicer for this application, and that's one of these NanoVNAs. I have a much nicer VNA, but this NanoVNA is pretty cool for just setting up quick experiments on. Now it's already calibrated, and to be honest, I'm just looking at the frequency response here, so I don't need to do anything too exceptional here. So I'm just going to pop the NanoVNA on, and what you're going to notice is if I hold the NanoVNA up, you can see I've got a lot of traces here, but the blue one is the trace that I'm interested in. So let's actually just look at that trace only. So that's the transmission trace. So it's measuring what's coming out on what's coming in on port 1, given I'm generating something on port 0. And what you'll notice is we're down at this line here, and each one of these divisions is 10 dB. So we're 10, 20, 30, 40, 50, 60 dB down. So that is what I expect from this attenuator. And then I see a rise up, but this rise up here is actually because of the noise of this VNA. So it really works well up to 300 megahertz, but then up to 900 megahertz, which is this point on the right hand side here, you start to get noise. This VNA actually has can actually be set to higher frequencies. So let's just quickly set it to its maximum frequency. if we have a look at this, I've just set the frequency, the stop frequency up to 1,500 megahertz, so 1.5 gigahertz, and you can see this noise of this VNA is really picking up, and we don't get any better than just under 20 dB once we're at the upper frequency range. But we'll still be able to see the response of this attenuator. So what I'm going to do is quickly put 14 volts into this thing. So I'm going to put plus 14 volts there, and then attach minus 14, well, it's ground, sorry, here, here, and here. And then turn that on. And what you'll notice is we actually see a flat response now, roughly 0 dB. A little bit of, we're seeing some overshoot here, but that's just noise in this VNA. I didn't really calibrate it at these upper frequency ranges. So now, as I remove different attenuators, you should be able to see the effect on that trace. So for example, if we take the 10 dB attenuator out, see it drops by 10 dB. If we put it back in and take the 20 dB attenuator out, yeah, we're down 2 divisions. And if I take the 30 dB attenuator out, we're down 3 divisions. So everything looks like it's working pretty well here. So so that's 40 dB, yeah, and then finally 60 dB, which you can see down this bottom end where the noise of the VNA is fine. So this attenuator looks pretty good. So there's nothing wrong here. We'll have to move further down the signal chain to find what's wrong with this unit. Okay, so after it comes out, the signal comes out, this attenuator, this slightly more complex piece of coax actually takes it out here and routes it to the first mixer. So you can see there's an unattached port over here, and that's the RF in. So into the first mixer assembly, and here it's mixed with a local oscillator, which is coming in here. That local oscillator is this metal container you see here. So this is your voltage controlled oscillator, with the output coming up there into this local oscillator in. It's mixed in here and filtered before then coming out as an intermediate frequency here. So it always comes out here at 2.124 gigahertz. That is then sent through I think this is a filter. I'm assuming this is a filter before entering into this unit here, which I've been looking up online, different RF components, and it looks like an isolator. I think there's something written on the other side there, but I haven't pulled it out yet. It's quite hard, by the way, to pull this thing apart. To get this attenuator out, I think I had to remove the first converter assembly. So what I'm going to, well anyway, it comes through this isolator, which is designed to stop mixing products coming out of this second mixer and reflecting into the first mixer. So you've got this isolator there to do that. It comes out around into the second mixer. Here it's mixed with the 1.8 gigahertz signal coming from the frequency tripler before coming out this second converter out here and going into the third converter / mixer in the back of the unit. There's your 600 megahertz in, and what you'll notice is there's an 8 volt in here as well, and that's basically on the same control cable as the attenuator. The YIG, the local oscillator, is controlled by this cable. Now I have to say, if you're trying to remove this, you have to remove the analog board first, otherwise you'll bend the pins trying to get this out, so watch out for that. So what's our strategy now? We're pretty sure that this attenuator is fine. What we should do is probably check whether this first converter assembly is fine or not. And if you look, there's no active components here, there's just this attenuator. So what I'm going to probably do is directly inject this IF, replace this IF out. So you see the second converter in. I'm going to disconnect this and disconnect the IF out here, and I'm going to reroute the IF out from here into the working front end, and that will let me know no wait, I'm going to route this in here, and that will let me know whether it's the second converter that's at fault or if it's the isolator, the filter, and the first converter that's at fault. Okay, so here's the next stage. What I'm actually trying to do is jumper between these two bits of a kit. So let's see if I can explain what I've done. This is the original front assembly, the one that has a problem. What I'm doing is I'm taking the calibration signal out. I've bypassed the front attenuator, primarily because the front attenuator and the second stage share a cable. So I actually just want to use the second converter over here, and that power cable shares a cable with the attenuator. So I've bypassed the attenuator, I've got the calibration output going straight into the first converter assembly. Then I've got the LO on that first one attached to this first converter assembly. It comes out through its filter and its isolator, and before it gets into the second stage, I inject it into the second stage over here, along with the second converter output being pulled out and the 600 megahertz inputs over here, and the power as well that is all attached on the second stage. So I've split just here between the isolator and here. So clearly the problem is in the first half. So it's either in this cable here or here. So what I'm going to do next is, what am I going to do next? I'm going to actually try. I'm wondering if it's the LO. You know, I don't have a spectrum analyzer that can reach the frequencies of this LO, so I can't tell if the LO is okay at this point. Wow. Okay. So it's the LO that's dead. This LO died, which I totally didn't expect. I just completely didn't expect. So I think what I've got to do here is I've got to put everything back together on the broken unit, except try the LO from the working unit in here and see if that works. That's now the proper test, because right now what I'm using is I'm using everything that works in the working unit over here. I'm using everything but the first mixer. I'm using the first mixer from over here. So this first mixer isn't broken. I thought it would be the first mixer that's broken, but it's clearly not. I'm getting my comb through, so everything's working there. It only started working though once I included the LO from over here. So it must be that my LO is broken, which is really quite surprising. I didn't know you could break LOs. So I wish I had the spectrum analyzer. I could have just totally, with a higher frequency range, because then I could have totally found that a lot quicker. I could have just checked the output from this first LO. Right, so what I'm going to do now is reassemble as much as I can this front assembly here apart from the first LO, and see if the second mixer and everything else is working when I just have the first LO swapped out. Okay, so what I've gone and done here now, this is it, the system working. This was the broken assembly. Everything's being routed through this front assembly. I mean, the attenuator's not in there because actually getting at things like this front oscillator is really challenging with the attenuator in place. So right now everything in here is being used, except what you'll notice is I've disconnected the LO. So this front LO is not there, and I'm using the LO jumpered over from that side. And sure enough, there's my output. So it looks like my LO failed. Yeah, just it happened to be while I was using it that the LO failed. So what I'm going to do now is pull out this LO and see if I can see inside if there's anything that might have gone inside there. Also check for continuity on this cable, see if this cable's any good. I could just swap the LOs out, but I'm a little bit tempted to try and fix the LO if I can. But that's brilliant. I'm really happy that it's the LO, because as far as I know, the adjustment procedures for the LO are pretty much non-existent. There might be an amplitude adjustment, but I think that can all be handled by the normal calibration pass that these things run through. So that's a great result. We'll pull that LO out and see if we can repair it. So here's the unit with the replacement yig, and there it is, working beautifully. All I've got to do now is put the attenuator back in, install this in again, and we can start looking at alignment and then adding a tracking generator. So let's get on to that. So now that everything's back together, I'm actually just running it through a cal. I'm mainly using the cal amplitude and frequency setting as a quick checkout of the unit. Because what I've gone and done is I've started the modification. So just behind this counter lock, there was a terminated LO tracking generator output, and what I've done is put some semi-flexible coax on that and taken it out to the back of the unit, and I've moved the terminator that was on it onto the coax back there. And my plan is eventually to install a bulkhead kind of connector there, but for now I just want to see if this thing works. And it seems to be going through the cal just fine. There's no issues yet on the frequency and amplitude calibration. So it's, you know, beavering away, testing itself against the calibration output. So I think we're okay. I think that simply just moving that out hasn't caused any problems. Well, what we'll do now is we'll take a look at the tracking gen I'm going to attach and see if we can get it to track with this spectrum analyzer. Actually, I'm not going to install the tracking generator. It turns out I've bought the wrong one, so I'm going to have to actually reverse engineer it to make it work with this spectrum analyzer. So all I want to say is thanks for watching. I've got a load of extra stuff at the end of this video. It's mainly about details or the failed repair of the local oscillator, but nothing particularly interesting. Thanks for watching. Let me know what you think about it in the comments, and see you next time. So inside this little case in here is the YIG oscillator. So this sits in here like this. You have to undo all 4 screws to actually get it to pop out. So there's the block. And opening this up, the first thing I noticed is that's a pretty loose connector. So do you know what? There's almost nothing to go wrong there. A couple of resistors, a diode by the looks of it. No, 2 diodes and some caps. And maybe this here. So do you know what? I'm just going to push that in. Oh, what am I doing here? Oh, it actually comes out. Oh, the whole block comes out. That's kind of cool. Well, we've got to see now. Right, okay. Oh, look at that. That's a pretty cool module. That's a pretty cool block. So we'll reseat this. We'll put this back together. Well, what we'll do is we'll try and turn this on again now. We'll connect this back up to the analog board. We'll just see if it really was, because that was a little bit loose there. Yeah, and then if not, we're going to go down and test these capacitors in the diode. Okay, so now we've got the LO block just sitting out there in the open, and yeah, still nothing. So if I wobble this, yeah, we're getting nothing. So percussive maintenance. Yeah, still something dead here. So I'm going to pop this off and check those capacitors in the diode and just see what's going on there. So I took a look at this, I checked the resistors, they're measuring 4 ohms, and as far as I can tell that's what the colour band's been. They've got they're one of these weird ones where you have yellow, blue, yellow, then a silver, then a brown, and the brown is the tolerance. I thought at first the brown might have been the temperature coefficient or something like this, and it was a really old one, but no, it's a silver. So I think what we're seeing there is 363 divided by 100, so around about 4 ohms, and that's what I was getting out there. I also measured the diodes, and they had forward voltages of 0.7 volts, so everything looks fine. I checked the capacitors out. They looked fine as well, so their dissipation factor was about 0.4. Just on the off chance it was them, I replaced them anyway, but it still doesn't work. So I think the only thing I can really check is that this cable's okay, and before I actually just give it in. But I think I'm going to probably just have to swap out for the YIG from the other unit. Yeah, so there we are. I'm an idiot. I didn't connect the isolator to the second converter. Everything I just said is invalid. Right, let me go re-put that coax in and see what difference that makes. Okay, so I think that's the final nail in the coffin for this YIG oscillator, at least as far as I know. I'm going to probably tear it down at the end of the video and have a look inside and see if there's anything broken in there that I can repair, but at least nothing's happening here. Oh, why wait for the end of the video? Let's tear it down now. But I will replace that YIG oscillator with the one from the other unit. The thing I was doing just before is I forgot to attach this piece of coax between the second converter and this isolator, so no surprise I wasn't seeing anything. But yeah, okay, so let's pull apart this YIG oscillator and see what's going on inside it. So the insides of this YIG oscillator are actually exceptionally beautiful. There's some components I could check there, but I honestly do not know what I'd replace them with. So there, I think there's some capacitors clearly here. I can't see any obvious damage though. So what I'm going to quickly do is have a look at this under the microscope. So here's the top of the unit, and if we zoom in, you can see it's filled with just some really gorgeous bits of RF circuitry there. So that you can't quite see. Let me just try and focus a little. There's a lovely little coil of golden wire there between those two pads. And what else? Oh yeah, and there itself is the actual yig. So I'll just bring that into focus. So just underneath that golden kind of cover at the end of that white rod is the actual yig oscillator itself. So just there in the center of the frame now. And you know what, looking around this thing, there's nothing I can see that indicates that this thing's broken, but do you know what, I just wouldn't know what I'm looking at when it comes to this stuff. Such a beautiful, beautiful item. So you can really appreciate the detail that's gone into this. Okay, and there's one other piece to this, which is this part here. That's really quite nice again. This is just a magnetic coil though, just part of the base. But everything kind of looks okay here. So that's the base itself. Sorry about the exposure there. Okay. Yeah, nothing doing. Very nice. Back to the main event. Okay, one thing that I haven't done is showing you the underside, so we'll have a quick look there. You'll see the underside's actually kind of a bit more interesting from a digital point of view. What you have here, this is a front card reader. Now the unit will operate without this. I don't need this card reader, but it is a useful thing to have because you can get personality cards and they actually add additional features to the unit. For example, you can actually get a load of stuff to help you with electromagnetic certification, so looking for noise and so on. Here we have another RF board. I'm not exactly sure of the point of this. I mean, it has this sampler in here, but I'm not sure where that sampler is going. Where does it? Okay, so I figured it out. It turns out this RF sampler here, it actually goes to this front assembly here, and what it does is it's connected to this counter lock allo out here. So its purpose is to actually measure the frequency of the first allo in the first mixer, and that's to improve your frequency resolution. So all the other stages of mixing use a fixed frequency, so we can tune that at factory, but the front allo is a voltage controlled oscillator to let us actually tune to a particular frequency while we're scanning or sweeping through the frequency response of this. There's a couple of other things in here that are interesting. One, we have a GPIB board down here, so this actually the unit will operate without this as well. This board, it was actually taken out the parts unit. I didn't have one originally in this unit, so that's one of the other reasons why I bought the parts unit. But underneath underneath these two boards that you see here is actually the logic board. You can see a row of status LEDs up here. They tell you whether the logic board's working or not. In normal boot up, all of these LEDs are off. It's quite interesting to look underneath the GPIB board, so let's take a look at the parts unit. Underneath the GPIB board, you can see we've got this battery here, and this battery is essential. So this battery backs up the calibration constants in the non-volatile RAM. So it is a battery backed up RAM. This super cap up here, I think, holds a charge while you're changing this battery out. So I think you don't have to have this thing plugged in while you're swapping this battery over. But what you should do is, if you've got this unit open, check your battery here. This one's at 3.6 volts. That's absolutely fine. So here I want to show you where you can get the service level calibration data. If you hit cal and then you go to service cal, then you've got flatness data here, and if you hit edit flatness, you actually get the a little readout of what the actual corrections are for I think it's the log amplitude, the attenuators at the back of the unit, just before the log linear amplifier. And what you see is there's a series of points with a decibel correction here. So this is 4 megahertz minus 1.08, and if you just step up through them, 41 megahertz minus 0.57, 78 megahertz minus 0.13, and so on, then you can actually see the correction constants that you need to take care of. So I'm going to actually use this video as my record here. Hopefully you can see it all. 300 megahertz. I'm just going to wait for that sweep to work. So there's actually a table in the service manual if you want to pull this out. But as you can see here, the frequency response is about a decibel out. Up to about a gigahertz, and then we really start to see the corrections kind of take off. So if that battery at the back fails, this is what you're going to lose. And then once we get up to 1.817 gigahertz, actually that's where we run out of calibration data. That's one lot of calibration data. So to access the attenuator calibration data, you have to hit cal, go to service diagnostics, and then go display cal data. And so these are the actual error constants for the attenuator. Where is it? The attenuator. The first 5 corrections in the error column. So it's these guys here. Okay, at the back we're missing a few things. You can see LO output and these other things. These are to do with the tracking generator. As far as I can tell, these ones here, like the sweep and tune output and this LO output up here, are actually to do with the internal tracking generator option, which we don't have. So what I'm going to do later is actually put a jack there, an SMA jack in there, to actually get to the first LO, so we can run an external tracking generator. You'll notice we have a few other things. The GPIB board actually gives us an external keyboard plug, as well as this HPIB, GPIB port here. And actually on my unit, there's a monitor out, there's a BNC that's meant to be here, and it's quite clearly snapped off from my unit. So I'm going to add a BNC port there as well, so that I can monitor the output. And I think that's it. Oh, we've got an aux IF output, that's interesting. So I could probably put something on here to listen to a tuned to frequency. So these are quite fun to play with. We might do a little bit of playing with these later. Oh, there is one other thing you've got to watch out for. So if you might get a ref unlocked error at the front, and it's because these two things need to be linked together. So you've got a 10 megahertz reference output here, and then your external reference in here. If you don't put coax in here, you've not got the frequency stability again. So you need a short section of coax from here to here to actually get rid of that ref unlocked warning. So watch out for that as well. Oh, and there is one other thing. This aux interface down here, although it's a nice 9-pin D-sub connector, it is not serial, and it is not a monitor. It is something completely different, including with up to 15 volts coming out of this thing. So don't just go randomly plugging stuff into there. You're going to have a bad time. Right, and that's it. So let's go and have a look at the front end.